Hello, yes. I'm going to be talking about miniDusa, an extensible finite-choice logic programming language. I'm Ari. This is joint work with Zach, who is here. Yes, so if you want to talk about miniDusa, we should first talk about what Dusa is. Dusa is another logic programming language like Datalog. Programs consist of facts and rules that you can use to deduce more facts until you can't deduce any more. We're going to talk, as an example, you can consider this graph. This graph you can encode as a bunch of facts that look something like this, and you can say that an edge from x to y is the same as an edge from y to x to ensure that the graph is undirected. And if you want to look at graph reachability, you can define a reachability relation that says that if you have an edge from x to y, it's the same as having, you can reach from x to y, and if you can reach some node and you have an edge from a node to another node, you can reach that one too. Then we wrap this in a logic block and run it into our solver, which gives us a solution that has some facts in it, and this will look like a series of facts that says that you can reach from A to B, A to C, etc. One thing that Dusa adds on top of the data log-like semantics is finite choice, where you can describe mutually exclusive choices between several values, where you can get several solutions that each reflect different choices that were made. If you look at this graph, you can have a relation color that takes a node and assigns it a color that is red, green, or blue. And this will give us a solution that looks like this, where you can see a color is effectively a function that maps a node to a color. And if you want to look at this graphically, you will get a graph like this. And you can get another solution that might look like this or like this, which is not a very interesting computation because this will compute all 3 to the 5th possible colorings of this graph. And we want to forbid the ones that aren't valid. So using the forbid rule, we can say that if there's an edge from x to y, we forbid that they have the same color, which will throw out that solution and get only the ones that are proper colorings. So these are all the features of Dusa, and we want to talk about what we added on top of this. So we will talk about the implementation of miniDusa. We implemented miniDusa using syntax-spec, which is a meta-language in Racket for defining extensible DSLs. You define the language grammar and the binding structure, and from that you get a macro-extensible DSL, IDE support, and interoperability features with Racket for free. And the way that we use syntax-spec is that we specify our grammar, and that expands our source syntax into a core where we can do static checks on it, and then call our runtime functions that give users our solutions. So as we talked about, we have macro extensibility, which you can use to take a graph that might be complicated to describe and express it using a more familiar syntax for people, like an adjacency list. This is just a syntax parse macro that you implement using any normal macro, like scheme macro. Macros also allow us to abstract over encodings, so you can go into the implementation of this macro and change what it does, and you can use that for hiding implementation details and making things more efficient. And one cool thing that we get from the macro system is that we can implement the demand rule that we saw earlier as a macro. The macro just deduces a contradiction if the premises that we provided are met, and that causes the solver to throw out that solution. One thing to note here is that every use of the forbid macro will make a fresh relation called OK that doesn't conflict with any of the other ones that were previously defined. Dusa hard codes these into their solver, and we don't have to do that, and we can just define them on top of our core language. Another thing that we get from syntax-spec is that we can import functionality from Racket, and And we do this in terms of the import keyword. We can import a function that might be doing something like if you have facts about people and you want to do something with dates, doing date parsing in logic programming is really hard, but in Racket it's really easy. You can just define this function and you can use it inside miniDusa as if it were just a functional relation that we defined. And this ensures that you can do the thing that is easier to do in either of the languages, and you can interoperate between them. And on the other hand, when we have functions, you might want to also import data from Racket, and we can also do that. You specify that you want the person relation to come from outside, and when you call the program, when you call the solver, you provide it some facts. This can be fetched from the internet, from a database, whatever, and you're effectively operating on external data using external functions and using miniDusa as a subroutine, which means you can use language-oriented programming where you can work on problems that are easier to express in Racket, and easier to express in logic programming in miniDusa, and freely choose the right tool for the job. And we have several other features that we had to cut for time, like open rules for optional choices, demand that is the opposite of forbid, where you can require that solutions match several constraints, like imports for macros to use within their local bodies, and several in progress features like Racket APIs that are easier to use, etc. Yeah, that is the talk.
Thank you. Any questions? No? Could you go back to the previous slide? Mm-hmm. So I would like to, oh no, the future work.
Oh, yes.
Yeah, I would like to hear more about what the improved Racket API means.
Currently, we have we haven't done a lot of work into the API part of this. We have a function that will give you a stream of solutions, and it's kind of on the user to search for what they're looking for. And it would be easier if you can describe the shape of a fact, and you can be like, I want to check, for example, that you can query the specific color of a specific node or something like that, which you would have to do manually otherwise.
Okay, thank you. Any other? Yes?
What is the actual implementation of miniDusa look like? Are you using kind of a traditional naive data log evaluation procedure? Are you using like a magic sets kind of optimization? Or is it somewhere in between?
Yes, that is the mini part of miniDusa. It is an extremely naive solver.
Great, thank you.
Hi, I was wondering, why do you end up having to use the import form rather than just having if it's a Racket binding, it's just magically available?
This is the way that syntax-spec operates. We want to define a specific class of variables that are available to use inside our logic block. And if you want to bridge across to the Racket world, you have to have some kind of form that defines them.
Okay, you didn't just want to everything is available because that would, okay, thanks.
Good. So, thank you. Now